Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenters today are Eli Datma and Jacob Hendrickson. Eli is a thermal and CFD engineer at Thermal Analytics, where he develops thermal and EOIR models for defense and commercial applications using Titherm, MuSES, and Cotherm. Based in the Calumet office, Eli specializes in creating high-fidelity scene simulations that support a range of use cases, including AI/ML algorithm development. He began his career at TAI as an intern in 2020 and joined full-time in 2021 after earning his BS in mechanical engineering from Michigan Technological University. Jacob is a thermal and CFD engineer at Thermal Analytics, where he focuses on thermal and IR modeling for both commercial and defense applications. He has extensive experience in full vehicle thermal validation, EOIR scene simulation, and synthetic environment creation using MuSES, including texture mapping, terrain classification, and realistic material assignment. Jacob also supports AI/ML development through the generation of accurate scene data and target representations, and has contributed to human thermal modeling through the creation of mannequin models and a novel infant physiology. He joined TAI in 2020 and holds a BS in mechanical engineering and an MBA from Michigan Technological University. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll be sending you the recording link when it becomes available. And with that, Jacob, if you're ready, we may begin.
All right, thank you, Chris. Hello, I'm Jacob Hendrickson, and today I would like to talk about MuSES's electro-optical infrared capabilities for AI/ML applications. So to start, I'll run through the agenda for today. First, I'll give a short AI/ML introduction. Following that, I'll introduce MuSES, our flagship electro-optical infrared simulation package. After that, I'll discuss how Thermal Analytics can create synthetic scene terrains. Following that, Eli will discuss how you can create image datasets with our process automation tool, Cotherm. And then finally, he'll show some internal working examples and some of the progress our customers have made using our tools. AI/ML has become a very popular area of research in the past few years and is growing more prevalent every year. Precedence Research, a market research organization, recently released a report which estimates that the AI/ML market within the defense market is expected to grow 2.6 times within a decade. With previous ML algorithms showing high performance in tasks such as target detection and recognition, and this estimated growth over the next decade, it will become increasingly important to make sure that the information that is being used to train these tools is high quality. We know that these sorts of deep learning approaches rely heavily on large and diverse data sets to generate accurate statistical predictions, making the availability of high quality and sufficiently extensive image data sets a key limiting factor. Data sets in the visible spectrum are easy enough to come by, but it is very hard to find data sets large enough to train on in the IR spectrum, from near IR to long-wave IR. So often the acquisition of suitable image data sets can be a limiting factor for how these approaches are used. Thermal Analytics has a history of IR scene simulation and can help you if your desired imagery cannot be easily found, capturing your own imagery is too resource intensive, or if you're unable to obtain your desired targets, possibly because they are either foreign made or adversarial made. Throughout Thermal Analytics history, we have developed an extensive model database. This database includes tracked and wheeled ground vehicles of different uses, airborne targets including jet aircraft, helicopters, and drones, maritime targets of multiple sizes, and personnel in numerous poses. We can use these target models to help fill potential gaps in IR imagery space by utilizing MuSES, our flagship electro-optical infrared software. MuSES is a thermal solver and electro-optical infrared rendering tool which takes inputs such as a 3D CAD geometry description, part material thicknesses and thermal properties, and component heat sources, as well as boundary conditions such as the sun location, the sky and background for radiation exchange, and air temperatures and speed for effective heat transfer to properly set up the analysis environment. Once these are combined, we can get a physical temperature prediction of the target. Sensor images, which can be specular or diffuse, as well as spectral or across a broad band. And we can also get contrast metrics such as delta TRSS and contrast radiance. Being able to gather all of this information from one software is what helps make MuSES such a powerful tool for those who care about the I/O spectrum. However, there is still more that MuSES can do. MuSES can model exhaust plumes for added signature accuracy. Oftentimes, these plumes can be hotter and/or larger than the hard-body target itself, so ignoring it can underestimate the overall signature. To do this, MuSES imports volumetric CFD results from an external analysis and will calculate the plume radiance when creating rendered images of the target. This plume radiance is only calculated for ray tracing paths between the scene and the sensor which pass through the area of the imported CFD results. We also support the inclusion of CO2, H2O, and carbon soot as species within the plume. MuSES can also model human targets and their IR signature. In order to do this, Thermoanalytics has worked to develop an accurate human thermoregulatory model which incorporates metabolic heating, shivering, respiration, sweating, and vasomotion in order to accurately predict tissue and core temperatures. Laser illumination is another capability of MuSES. Hard-body and component heating from a directed energy source can be included in the thermal simulations, and users can specify laser parameters to include a narrowband source in the sensor renders. We can also handle IR simulations of satellites for various orbiting payloads and sensor platforms. This can include electrical thermal simulations of battery systems, solar panels, internal electronics, as well as passive and active thermal control systems. MuSES also offers some flexibility on the amount of detail used in scene simulation for both the target and the background. We can use the default background option available in the software, which automatically creates an infinitely large ground plane under the target. A faceted background can also be implemented, where we assign elements as background and use geometry to represent different types of discrete clutter. A higher fidelity textured background can be another option, where we use satellite imagery to create a ground truth representation of the target area. We can also create composite imagery, where we simulate the target in MuSES and then insert it into a measured background that's radiometrically calibrated. And we are partnering with other software companies such as Dursig and Octal to allow you to insert our target models directly into their scene simulations. The textured terrain approach has been something that Thermoanalytics has been investigating and developing in the recent years, and I would like to discuss it further. Thermoanalytics has developed an in-house process to create realistic-looking textured backgrounds via open-source information, such as satellite imagery and digital elevation maps. Here we can see one example of such a background. On the left, we have a satellite and topological representation of the target area, which is drawn in yellow. And on the right, we have the terrain seen in MuSES after it has gone through our textured terrain creation process. This process captures topological relief and, on an element basis, automatically separates different types of ground cover from bush, tree, gravel, dirt, sand, etc., which are represented by different colors in the model. Due to the open source information that is fed into this process, it can be used for almost any location. Thermoanalytics is actively researching and expanding this process and its capabilities. Here we can see some sample images using this background creation process. These images are in the mid-wave and long-wave IR spectrum and were simulated at multiple points throughout the day. The difference in the color throughout the background are due to using a computationally efficient way to model background clutter and variation without using a large number of surface elements to explicitly model objects in the scene. In addition to the previously shown backgrounds, we have numerous terrain possibilities within our database that range from the urban to the rural and from deserts to mountains. To help speed up the terrain creation process, Thermoanalytics has been developing a tool to help automate the process. Using the tool, a user can quickly create custom scene geometry from satellite imagery, either using digital elevation data for a real location or using procedurally generated elevation data. The tool also assists in the process of planting vegetation, trees, bushes, shrubs, and buildings into the scene. Next, Eli would will discuss image dataset generation using Cotherm.
Awesome, thank you, Jacob. So as you can see, there's quite a bit of information that goes into making a target model, and adjusting all that manually to create an image dataset can be quite tedious. However, we can automate some of that with another one of our tools, Cotherm. So inside each model, we have the geometry of a target, whether it's something that you bring in on your own or from our existing database. We bring in optical surface descriptions and terrain descriptions that go in that scene. Then all of these models get fed into MuSES along with weather data and sensor parameters. And after that analysis, the synthetic images of a scene are generated. Those images can then be fed into an algorithm to give some deep learning output. And to generate these types of data sets, Cotherm is our tool of choice. So Cotherm is a co-simulation and process automation tool. It's often used for complex multi-physics simulations that require coupling multiple software packages together. However, it can be used to automate a repetitive process like MuSES thermal and infrared predictions over a wide range of variables. So the Cotherm user interface is shown here. There's a process flow chart made up of a series of simple tasks that run to completion. So we're able to provide a GUI-based path for generating these large IR data sets of interest in an efficient manner. And as of Cotherm 2025, a standard process, parallel BRDF rendering process, is available for generating a large set of BRDF renderings efficiently using parallel processing. The process automates the calculation of both the thermal and diffuse radiosity solutions if they are not already completed, as well as the BRDF renderings themselves. User inputs can be quickly set up to define one or more models to be rendered in the parameters that dictate which set of renderings will be generated. Along with the models themselves, a template BRDF configuration file is given, which will be modified with the parameters to be varied for each rendering, and all other parameters will be maintained from the template rendering. So during or after that process, a set of DAT or PNG files will be created for each rendering for each file. The images on the slide show a few of the images created by the standard provided example. Each output file is given a name that includes the rendering parameters used, which easily allows browsing through the images. And this file naming scheme can be easily customized if desired. So the process simply creates these files and exits. But Cotherm's process flexibility makes it easy to extend the process to organize or analyze the rendering results in custom ways. That includes passing the rendered images into AI/ML training processes used for target recognition or other applications. And these extensions are usually straightforward using built-in Cotherm features. And of course, thermal analytics technical support can also be engaged to help with the process automation. So as I previously mentioned, the output for the parallel rendering process can be easily customized to fit your desired needs. So besides the default output of the DAT and PNG files from the process, we can also adjust the process to output files required by some machine learning algorithms, such as image masks, human joint labeling files, target occlusion percentage, and JSON files for the image annotation. So you can see a few examples here on the screen. There's a human down here with a bunch of colored dots on their body, showing exactly where all the joints are. To the right here, you can see an image labeled by color of the background in blue, the road in green, the target in red, and all the trees in orange. And all of that helps with that AI/ML training process. To further enhance that image generation capabilities that we offer, we also developed a robust composite image generator tool that allows the user to combine measured background images with rendered target models. So example output images from the composite imager are shown below, where 3 drones are thermally modeled and rendered and then inserted against a measured sky background. So the target location is also randomized on this image. The target is scaled so the edges have a better blend into the background, and sensor noise and blur can also be added to better match the background imagery. Another addition is rotor blur. So our base thermal models show a static geometry. Moving parts are not visually modeled. An example of that is shown in the upper right here with the unmoving blades. So, however, this does not properly account for a sensor's integration time. In the bottom left, we can see 2 measured images. The one on the left shows a 360-degree rotor blur, and the one on the right shows about a 45-degree blur from each blade. And those different arcs are an example of 2 different sensor integration times. So to properly model that, we've added some Python code into that cotherm process to add the propeller blur into the renderings. So these are also blended into the background, and the blur arc angle is user controlled to exactly model whatever sensor you're modeling. So by combining MuSES and cotherm, we are able to generate large, highly accurate, and automatically labeled datasets, which can be used for training and testing various AI/ML tools, such as those for target recognition. These datasets can encompass anything from humans, ground vehicles, aircraft, UAVs, and maritime targets. So let's go a little bit more into the working examples here to see how these tools have been used in actual projects that we've been doing recently. So this project right here, we used our cotherm image generator process to generate about 205,000 images in about a week and a half. So this included geometric differences such as different vehicles and locations. We also modeled different engine states, time of year, time of day, and a variety of different sensor angles. To add to the randomization for training, those angles are all randomized in a normal distribution to give better variance in the images. As a bonus post-processing step as well, the process automatically throws out the images where the target is more than 30% occluded by things like trees or buildings. So another project focused on human detection in multiple terrains, including urban areas, desert, and woodlands. So we generated synthetic IR image data, which we then used to train an object detection algorithm. And these data sets included multiple terrains, ranges, and times of day as well. So here are some of the types of scenes that we used in training the human detection algorithm. As you can see, there's quite a bit of detail in the buildings and trees and ground. At the bottom also shows the variance we had in human models from different clothing, genders, human size, that all went into training this detection algorithm. So we then extended our testing to include measured imagery. So we trained the algorithm exclusively with synthetic data and then tested against a measured scene. And YOLO was used for this training algorithm. As you can see in this video on the bottom right, we observed many positive detections and good tracking of the human targets, some of which are detecting humans even through the trees on the left side here. So one other project focused on the automatic target recognition of ground vehicles and how sensitive these ATR algorithms are to multiple vehicle or variables in their training data when testing against measured IR images. So to investigate this, we created multiple simulated IR data sets, which encompassed many different training parameters, such as same as previously, such as target, sensor range, view angle, time of day. We also needed to find a measured set of IR images that we could then use for testing our trained algorithms. So that measured dataset that we chose is the DISIAC ATR dataset, which is publicly available. So we used 6 of these 10 vehicles, all of which were already in our thermal model database. So the ones that we didn't have matching models for, such as the SUV, the things that are crossed off here, we didn't use, as well as the T62, which actually broke down during the measured testing. We then qualitatively compared the measured images from the DISIAC dataset and our synthetic target models. So all these images were taken at nighttime. They were in the midwave at about 1,000-meter range. And as you can see on the right here, we see a very good agreement between the measured images and our predictions. And another metric that we looked at was a histogram of the number of pixels showing specific apparent temperature values between the measured and simulated data. This one looks at the T72. And this histogram also shows good agreement with the same spikes around the same points. And these images were masked, so it could be a direct one-to-one comparison between the targets rather than including any background differences. And here's another example using the 2S3, which matched the results very well between the DISIAC and our simulated data as well. This is a slightly smaller vehicle, more of a centralized heating point, just to get some more variance in our results looking here. So to do our sensitivity analysis, we use an AlexNet neural network architecture, which we trained with strictly synthetic data and tested only against measured data. So after investigating all imagery variable combinations, we found recognition rates up to 3.4 times better than random choice, depending on the variable conditions. These results are shown on the heat map on the left side of the screen, where the recognition percentage is visible, as well as the dark to light gradient for quick identification of highly performing models. So some of these variables include alternate background terrains around the vehicle, as well as tone mapping, which yields different levels of contrast in the training and testing images. And further work is always being done to increase these recognition rates and better understand the domain shifts from synthetic to measured data. Throughout this webinar, we have seen that thermal analytics can model these high-value targets on land, air, sea, or space across the IR spectrum. We can generate a large and varied image data sets of these targets, including synthetic background, which can be used for those AI/ML applications. Cotherm allows the fast creation of these data sets, combining that with our image generation process to make it a much easier process to set up as well. All these products have shown viability within the AI/ML workflow to substitute for measured imagery training data sets, both internally and by our customers. So that's all we have to show for this presentation. Before we move into any questions, I wanted to show this slide here. This shows a quick schedule of our remaining webinars that are in this 4-part series. This is just the intro to AI/ML. But if you're interested in seeing any of these other specific parts, then feel free to sign up for these as well. Any questions on our webinar?
Yeah, thank you, Jacob. Thank you, Eli. I can go ahead and open it up to some questions here. Is the scene creation tool available for use?
I can take this one, Eli. So the scene creation tool is still currently being actively developed, but if you reach out to your sales point of contact, we could talk about potentially getting a test of this of the tool itself. Just reach out to your sales contact, and they can talk about that with you further.
Excellent, thank you. Where can I find or download the parallel rendering Cotherm process?
So we send that out to customers who ask for it. I think that's also something that you would have to ask your sales representative for. Jacob, do you know if that's within the example files we send with the base software?
Yeah, that actually is in the
Oh, okay.
version 2025.1 release of Cotham now in the examples folder. Previously it was by request only, but now it's provided.
All right. Well, looks like that will do it for questions. So that will complete today's webinar. We appreciate you all for attending. You will receive a follow-up email later today containing a link to watch the recording of today's webinar. Again, thank you, Eli. Thank you, Jacob, and everyone for attending. And everyone have a nice day.
Thank you all.
Thanks.